Hey folks, we're going to talk about Newton's third law. And by the way, if you watched my previous video, I mentioned that we will be doing examples with Newton's second law. That will actually be the next video. I felt it was kind of important to interject and put Newton's third law and talk about that before we go on and do examples. Now, a couple things. First of all, Newton's third law is probably his most important of these three laws of motion that he developed, and I'll talk about that. It's also it's actually one of the simplest and at the same time one of the most confusing laws of physics for students. Eventually, I'll ask questions about Newton's third law on tests, and in an introductory physics course, maybe 10 to 15, 20% of the students maybe will get it right when I have an application of it. In a physics C class, which is for us at LT, a second year class, maybe, I might get more like half get it right, and that's good. so let me start with a quick review. Newton's first law. So Newton's first law says, hey man, things want to go in a straight line at a constant speed. They don't want to change direction, and they don't want to speed up or slow down. One example of a constant speed is 0. If you're not moving, you want to stay still. Newton's second law is the unless part of Newton's first law. Newton's first law says, hey man, things want to go straight line, constant speed, unless acted upon by a net external force. Newton's second law says, okay, if there is a net external force acting on the object is going to accelerate. And there's an equation for that. Acceleration is equal to net force over m, or you might know it as net force equals ma, and the a and the f have vector signs over them. So what's Newton's third law? Okay, well, I didn't write it out here. You can look it up online or on a textbook or whatever. And I'll start with what people learn the first time, which is not completely accurate. The first thing people will learn about Newton's third law is it'll go something like this. For every action, there's an equal and opposite reaction. Okay, and that's kind of right. It's missing something incredibly important, though, because when I think of action and reaction, I think of human traits. So, for instance, my brother hits me. What's my reaction? I'm going to hit him back. This is not what we're talking about here, okay? So I'm going to add the most critical word in the whole law and see if you can catch it. For every action force, there's an equal and opposite reaction force. Did you catch that missing word? Force, okay? So like going back to the brother hitting me thing, if my brother's knuckle hits my jaw, the reaction force would be my jaw hits my brother's knuckle. Now, why is this Newton's most important law, in my opinion? It turns out that this leads to other things. This leads to conservation of energy. This leads to conservation of momentum. Basically, what Newton's third law says is that things don't act. They interact. For every force, there's an equal and opposite reaction force. You cannot push on something without it pushing back on you. You cannot interact with something. You cannot act on something without it acting back on you. Everything interacts. This also means that every force, any force, always comes in pairs. Okay, and so that's what the examples I'm going to do here in a minute. There's no math today, but the examples I'm going to show you talk about those action-reaction force pairs. Okay, so the law is very simple. For every action force, there is an equal and opposite reaction force. So it doesn't matter what the two objects are, what they're doing. If A is pushing on B, then B is going to push back on A equal and opposite. In order to use Newton's third law or answer questions about Newton's third law, it's absolutely critical that you say whatever the first force or the action force is, you say it as a sentence. And the sentence should have a noun, a verb, usually a direction, which would be the adverb, and a direct object. So for instance, I push right on book. Okay. The reaction force is literally reverse the sentence. Reverse the direct object and noun. You switch those around and reverse the direction. So if I push right on book, book pushes left on me. This works every single time. It works every time. the critical part is you've got to be able to write the force as a sentence, okay? So I got a few examples that I'll draw and talk about. So let's say you're driving your car, and my car I know is extremely fashionable here, but there's my car. Let's say you're moving to the right, and let's say here's a fly, okay? And you run into the fly, okay? So one force would be the force of the car on the fly, okay? Which you consider that a normal force, okay? The reaction force would be the fly hits the car, so force of the fly in the car. And by Newton's third law, these two forces have to be the same. Now you might question this. You're like, well, wait a minute, there's no way. The car is so much bigger than the fly. How can the forces be the same? Okay. The forces are the same. The effects of the forces on the two objects are incredibly different. If I look at the fly, that force acting on the fly, which has a tiny mass, is going to produce a huge acceleration. All right, so that fly is going to accelerate and change direction really quick. Whereas that same force, notice the numerator in this fraction is the same, okay, divided by the mass of the car, which is huge, okay, is going to produce a tiny acceleration. So while the fly is going to experience a huge acceleration, the car you're barely going to be able to tell anything happen, even though the forces are identical. The other stuff in the equation is not, so that's why we feel different effects. Another example would be if you jump up. You push up on Earth, and the Earth pushes down on you. Those forces, or pulls, I'm sorry, you push down on Earth, Earth pushes up on you. Those forces are equal and opposite. That force acting on you is going to make you accelerate. That same force acting on the Earth's mass is something like 6 times 10 to the 24th kilograms. That same force is going to have is going to produce a very small acceleration on the Earth, okay? Now, that's my next example, by the way, is you got to be careful of action-reaction pairs. So let's say here's the ground, and here's you standing on the ground, and I ask you for all the action-reaction pairs acting on you. So the first thing you should do in a situation like this is draw the two objects separate. So here's the person, and here's the Earth, okay? So one force you might say is, okay, force of gravity. Okay, so here's the force of gravity acting on the person. What's the reaction force? Invariably, people will say the normal force, the force pushing up on the person. This is wrong. Okay, now those two forces may happen to be equal if you are standing still, okay, and not accelerating up or down or anything. Those forces may be equal, but they are not an action-reaction pair. You got to put the force into a noun, verb, adverb, and direct object. So force of gravity, how would you say that? That is the Earth pulls down on person. The reaction force is you literally just reverse it. The person pulls up on the Earth. Okay? That's your action-reaction pair. And no matter what, those two arrows have to be the same. Okay? Now again, that force will make you accelerate pretty quickly, at about 9.8 meters per second squared. That same force acting on Earth is going to produce a very tiny acceleration, negligible. Okay. Now, in this problem, with the person standing on the ground, there is a second action-reaction pair. The normal force. Let's put that in a sentence. The ground, or the Earth, pushes up on you. That's your normal force. Okay. What's the reaction force? Just literally reverse the sentence. You push down on the ground. And those two blue arrows have to be the same. Now, if you're not moving or accelerating in any way, then the blue and red arrows are the same. However, if you're in the midst of accelerating up or down, so for instance, let's say you're jumping up. While you're pushing down on the ground, the normal force would be bigger. The blue arrow will be bigger than the red arrow. So if you're pushing down on the ground, these two blue arrows get bigger, the red arrows don't change, and you accelerate up. Oh, and in the meantime, the Earth would accelerate down. Now, again, it's really tiny, but it's there. Okay. Now, other examples that you might consider. Let's say you have a tree. Okay, so here's your tree. Okay. Here's the ground, and here's an apple hanging from the tree. Okay. Let's talk about a couple action-reaction pairs. So one action-reaction pair would be gravity, force of gravity acting on the apple. Well, again, what's that as a sentence? That is, earth pulls on apple. What's the reaction force? Apple pulls on earth. Okay, those two arrows will be equal no matter what. Another action-reaction pair is tree pulls up on apple. That maybe be a tension force. Okay, what's the reaction force? Apple pulls down on tree. And those two arrows will be the same. Okay, those two blue arrows. Now, again, if the apple's not moving or accelerating, the red and the blue arrow will be the same too. But if the apple's doing something, swinging or something, then those won't be the same. Okay. Now, another example that gets confusing is, let's say you're pushing something up a ramp. Let's say it's a cart. Okay, we're going to ignore friction for this. And let's say here's you, and you are pushing. We got long arms, and you are pushing on the cart. Okay. Now let's say you're pushing the cart, so that's going at constant speed. Then you're pushing on the cart. So this is the force of you on the cart, and the cart will push on you. This is the force of the cart on you. And by definition, those have to be the same, okay? Now, does it matter if you're pushing, if the cart's moving up the incline, down the incline, if you're accelerating up the incline, if you're accelerating down the incline? No. Those two blue arrows will always be the same. Now, let's say you push harder to make the cart accelerate up the hill. Well, the cart will push harder on you, okay, which means something else has to be going on. And that's my next. I got two more quick examples. The next one is actually the quandary that Newton was supposedly, the story goes, is how he answered Newton's third law and how he answered his critics about it. So his critics would say something like this. Let's say you have a cart back in the day. Okay, so here's your cart, and you have a horse. Okay, please don't make fun of my horse, but here's your horse. Okay, there he is. And the horse pulls on the cart. Okay, so one force would be the horse pulls on cart. This is the force of the horse on the cart. The reaction would be the cart would pull on the horse. The force of the cart on the horse. And these two, by definition, according to Newton's third law, they have to be equal. Well, Newton's detractors said, how can this be? How could anything ever move if those two forces are the same? Okay. Well, what they weren't considering is that there's other forces acting in the problem. There's other action-reaction pairs happening. So first of all, what's the other object in this problem that we're not even considering? The ground, the earth, okay? If that horse is going to pull that cart, what's that horse going to do? Well, the horse is going to push on the earth to the left. This is the force of the horse on the earth. Well, what's the reaction? The earth is going to push the horse, the force of the earth on the horse, okay? And these two red arrows will be the same, okay? Will they be the same as the blue arrows? Well, no. If the horse is accelerating, the red arrow will be bigger than the blue. Now, if the horse is going at constant speed, or another example, if a car is going at constant speed or constant velocity, then those two arrows, red and blue, would be the same. But if the horse is accelerating, getting the cart going, then the red would be bigger than the blue, okay? Now, in addition, you probably have some friction on the cart, so that would be the earth. I'll call it force of friction, but that would be the earth tugging on the cart. The reaction force would be force of friction, the cart tugging on the horse, or on the cart, sorry, earth tugging on the cart. These two forces would be identical, but probably not the same as the other ones, unless you're going at constant velocity, okay? Now, if you look at each object individually, you come up with something pretty cool. If you look at just the forces acting on the horse has a net force to the right, so the horse will accelerate to the right. If you look at just the cart, okay, the blue arrow is bigger than the green, so the cart will accelerate to the right. And if you look at just the earth, okay, there's actually a bigger force to the left, so the earth will move slightly to the left. Now, again, the earth's mass is humongous, so that movement will be very, 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 very slight, but it's there, okay? So that's something else to kind of mention is, again, every force is an action-reaction pair. We interact. So if something accelerates right, that means that something else is accelerating to the left. Okay, now it may be negligible, the acceleration, because the mass may be huge, but it's there. Okay, So I hope that helps with Newton's third law. Again, the big key on Newton's third law is make your force into a noun, a verb, an adverb, and a direct object. I pull up on book bag. The reaction force is book bag pulls down on me. And those two forces have to be the same magnitude and opposite direction. They have no choice. So I hope that was helpful. The next video, I will do a bunch of Newton's second law examples, and have a good one.